Hello! We are glad to present TightCap 3D Human Shape Capture with Clothing Tightness Field. In this work, we address the problem of capturing a multi-layer avatar from a single scan of multi-view camera system. We propose a data-driven scheme, called TightCap, to capture both the human shape and dressed garments accurately with only a single 3D human scan. Our approach achieves the high-quality human shape and dressed garments reconstruction, as well as the further applications for clothing segmentation, retargeting, and animation. How to capture dressed human. Both single-view capture system and multi-view capture system can only capture the top surface of human. Therefore, traditional human reconstruction can only build one-layer model. There are many artifacts around the boundary of body and clothing. To address this problem, there are some works using inner body to generate two-layer model for simple clothes. Considering clothing can be loose, fitted or tight, we formulate tightness field to model this gap between clothing and body skin. Tightness describes the relationship between the body layer and the clothing layer. Ideally, the per-vertex tightness is formulated between body and top surface meshes with the same topology. In practice, we formulate this tightness equation to approximate this ideal definition. We can calculate the tightness field around the whole mesh. And importantly, to build an effective and reliable data-driven approach, we propose a new clothing tightness dataset of human scans. TightCap is a data-driven approach to capture both human shape and dressed garments, and finally generate a multi-layer avatar with only a single scan from multi-view RGB cameras. Specifically, we utilize a multi-stage alignment scheme to transfer the input 3D human scan into the consistent human template. Our scheme consists of the silhouette-based, point cloud-based, and per-vertex deformation stages to optimize the non-rigid motions, from the enhanced human template to the input 3D scan in a coarse-to-fine manner. To benefit the tightness prediction with the effective image translation network, we utilize UV mapping to map 3D features to 2D. Here we list two popular surface parameterization methods. We map the clothed 3D human body mesh with the consistent topology into a regular 2D UV image, which has been proved to be effective in previous works, geometry image and OptCuts algorithm. Overall, we utilize an enhanced simple-like human template for this multi-stage alignment approach. After the alignment, we map the 3D meshes into a hybrid 2D geometry image. Next, we estimate the tightness map and the clothing mask from mapped clothing feature with tightness prediction. Finally, in multi-layer reconstruction stage, we recover body shape and segment clothing from original mesh for various clothing topology to build a multi-layer avatar. To model clothing tightness in a data-driven manner, we propose a new benchmark dataset, which contains 880 dressed human meshes with both the body geometry. We build two different multi-view cameras system to capture 3D human scans. For the left, it is a dynamic capture system with 80 dynamic cameras to capture human performance. For the right, it is a static capture system with 80 DSLR cameras to capture high-resolution photo of clothing. With two capture systems, we propose a new benchmark dataset to model clothing tightness in a data-driven manner. We also annotate these dynamic sequences to support a pose-aware learning manner. For garment modeling, our dataset contains 228 high-quality garments, including t-shirt, short coat, hooded jacket, pants, and dress, ranging from ultra-tight to puffy. We have listed the details of our dataset at the last part of video. Next, we evaluate TightCap method on this dataset and other benchmark. Here we compare our results with other SOTA method qualitatively and quantitatively. Without the good initial state provided by the silhouette-based deformation, the non-rigid baseline cannot converge to a good result. This figure clearly demonstrates the effectiveness of each stage in our alignment scheme. Here we provide a qualitative comparison on 3 challenging cases with various clothing tightness and similar postures to get rid of the posture ambiguity. Our approach accurately reconstructs the human body shape by modeling various clothing tightness field effectively. We also evaluate our approach on other benchmark dataset. With only a single mesh input, our approach can still generate accurate body shape. We then visualize more static and dynamic results. Benefiting from our enhanced human template with rigged skeleton and the clothing tightness field formulation, we are able to infer the body shape and the various segmented garments, so as to reconstruct a consistent multi-layer avatar. Based on our high-quality multi-layer reconstruction, our framework can support various interesting applications, including immersive cloth ray targeting and clothed avatar animation. Here we show some multi-layer avatars with real-time physical simulation engine. Because our clothes are segmented from original mesh rather than template mesh. We also visualize a complex avatar animation with fluttering dress. To stimulate more research tasks, we introduce our TightCap benchmark dataset. It includes 80 capture views, various dressed human meshes, annotated body geometry, segmented individual pieces of garments, and reconstructed meshes. We believe TightCap dataset can support enormous 3D tasks, like human or garment reconstruction, garment segmentation, body shape estimation, and view synthesis. To achieve the free viewpoint video play, we also propose a 4D player to visualize dynamic mesh sequences. This player can easily change display view, adjust lighting direction, and switch rendering model. In summary, TightCap is a data-driven scheme to capture both the human shape and dressed garments accurately from a single 3D human scan of multi-view camera system. To support our framework, we propose a new clothing tightness dataset of human scans. The dataset contains a large variety of clothing styles, human poses, and corresponding ground truth human shapes. Welcome to view our project page. Thank you for your attention.